Welcome grade 12s to STEM in Action's Boost series. I'm Vicky Guyan, and today we're going to have a look at vertical projectile motion part 2. Right, remember some of the pre-knowledge we need to know. We spoke about our equations of motion from grade 10, as well as our quadratic formula from grade 11 maths, and then also our graphs of motion, which is what we're going to have a look at in more detail today. Remember that acceleration is equal to the change in velocity over the change in time, and velocity is equal to the change in position over the change in time. And so when we relate our tables, if we have a look at our displacement time graph, from the slope of our displacement time graph we can get our velocity. If we have a look at our displacement time graph, from the slope of our displacement time graph we get the velocity, because slope is change in y over change in x. So on our y-axis we have our displacement, on our x-axis we have our time. So it's displacement over time, which is velocity. From our velocity versus time graph, if we take the slope or the gradient there, we'll get our acceleration. On the other hand, if we look at the area under the graph, we would be calculating our displacement. Finally, from our acceleration versus time graph, if we have a look at the area under the graph, we are calculating the velocity. All of that you should know from grade 10 graphs of motion. We're going to have a look at a few different scenarios. Case 1, where we have an initial velocity upwards. Here, if we're throwing an object upwards, our initial position is 0. Right? And the object then moves up to a maximum height and then comes back down to its initial position over the course of a time. Remember that this object is going straight up and straight down, but time carries on, and that's why we get this curved motion. We can then have a look at the velocity versus time graph. Since we started with an upwards velocity, we start with the initial velocity, taking upwards it's positive, so we start with a positive velocity, but as it's moving up it is decelerating due to gravitational deceleration, and so we get a slowing down till it gets to its maximum height. Our velocity will be 0, and then it will move downwards and so have a negative velocity until it gets back to its initial position. Notice that the time it took to get from its initial position to its maximum height, and then from its maximum height to its initial position again, those time segments are equal. Finally, we can have a look at our acceleration versus time graph. And here, because this is vertical projectile motion, we know that for the whole motion, the acceleration is the acceleration due to gravity, which is always 9.8 meters per second down. We have taken down as negative, and so we can see on our graph here, we get negative 9.8 meters per second squared for the duration of the motion. Right, I've got my assistant here, Annalisa, so we can have a little look at what the graphs look like if we toss a ball up in the air. So Annalisa, you can go ahead and start recording. And so we toss it. Okay, so we can see nicely here that our displacement time graph, we got a nice curve. Notice that although the graph is curved, the ball went straight up and straight down. It didn't curve its motion. The x-axis is displaying time, so time has gone up as the displacement changed, and that's why we get that curve. For our velocity graph, what we would normally see in our exams is it starts from here and moves down, right, when it is actually in projectile motion. But we first had to cause that projectile motion, and so here at the beginning we've got where we gave it a velocity, and then once it left my hands, it was now under projectile motion, and so that's where we get our velocity here. Started with an upwards velocity, decreased here to its maximum height. Have a look how the graphs correlate. Here where it's at its maximum height, its velocity was 0, and then it came back downwards with increasing velocity in the negative direction. So we get negative velocity, and over here what happened, I caught it, so I quickly caused the velocity to stop. We can also look at our acceleration graph. We can see that at the beginning here was where I gave it acceleration, I gave it its initial velocity. So we're ignoring that part because we just want to look where it was actually under projectile motion. So once it had left my hands, so we're looking at this part here where we can see our acceleration is around -10 meters per second squared. And what happened at the end here is where we caught it again, and so that's why we get that bump there. What you would normally see in your tests and your exams, the textbooks even, is just this straight part here, because in our exams and our books, we are looking particularly at the projectile motion. So we're not looking at what effect I had on the motion, and so that's why we're just looking at this middle part here. Case 2 is when an object falls from rest. So our initial velocity would be 0. If it's falling from rest and we're still taking up as positive, down as negative, our initial position is 0 and it moves downwards, and so we're getting a negative displacement. That's why we're on the negative side of the graph. Remember, it is falling straight down. The reason we get the curve is because time is going on. And so this object is falling straight down over time. If we have a look at our velocity versus time graph, our velocity, it starts from rest, so our initial velocity is 0, and it's moving down in a negative direction, and it is speeding up as it moves down, and so we get this velocity increasing as it goes down. And finally, we look at our acceleration versus time graph. And again, this is projectile, and so our acceleration is still 9.8 meters per second down, and so we get the negative 9.8 meters per second downwards. Case 3 is if we throw an object downwards, so it has an initial velocity down. Here, our graph of position versus time looks very similar, just maybe a bit steeper as we have more of an initial velocity, so a quicker change in the beginning of the position. Our velocity versus time graph now doesn't start at 0, we now start with a velocity. Because we take down as negative, we've put it here as a negative velocity, and then it is accelerating downwards, and so we get this straight line graph forming. Finally, we can have a look at our acceleration in this case. Again, we are still dealing with projectile motion, and our acceleration is still 9.8 meters per second squared down. So just to summarize all of that, for our position versus time graph, we can see how it changes. We notice that we're always getting a curved graph. If it is moving up and down, we then get a curve for the upward motion and a curve for the downward motion, as in case 1. If it is just moving down, we just get a curve for the downward motion. Remember, in all 3 of those cases, we took up as positive and down as negative. And remember that displacement is a vector, and so we need to bear that in mind when we're working out displacement. Our velocity time graphs are always a straight line graph. For case 1, we saw that we started with an initial velocity upwards, so a positive initial velocity, and it then got to a velocity of 0 at its maximum height and went in the other direction. Where case 2, it started from 0, but then accelerated downwards, and case 3, it started with a negative velocity and accelerated downwards. Notice that the slope of the velocity versus time graphs has the same magnitude. So the gradient is the same for all 3 graphs, because remember, gradient of a velocity versus time graph represents the magnitude of the acceleration. And all of these are for projectile motion, so our acceleration is negative 9.8 meters per second squared, or 9.8 meters per second squared down. And so then you will see that our acceleration time graphs look the same for all 3 scenarios, because the acceleration for projectile motion is 9.8 meters per second squared down. Right, there's just one add-on to case 1. Case 1 was when the object moved up with an initial velocity and came back to its initial start point. But sometimes this could happen that you throw an object up at the edge of a cliff or on top of a building, and then the object can fall below the initial starting position. And so our graph looks quite similar in the beginning to case 1. We can see that the object moves up to its maximum height and then comes back down over here to its initial position, and then the displacement is in a negative direction, so it continues to fall further down. Again, in this graph, we're taking up as positive. If we had to take the ground as our reference point, then when it reaches its final position, it would be on 0. So our initial position would then start some positive point above the ground. Notice the shape of the graph doesn't change between these two. It's just where the graph starts and finishes in terms of what our reference point is. So in the first graph over here, our reference point was our initial position, was our 0, and in the second graph, our ground is our 0. In both cases, our velocity versus time graph looks the same, and so we start with an initial velocity upwards. It then gets to a velocity of 0, starts to move in the negative direction. Over here, it is where it reaches that initial position, and so we know when it reaches the initial position, the velocity will be the same as the initial velocity upwards, but in the opposite direction. So same magnitude, but opposite direction, and that's why we've got our negative. And then it continues down, so it continues increasing its velocity and accelerating further. And we know that our acceleration graph will look at the same as what we have looked at previously, as it is still a projectile under gravitational acceleration. Now let's have a look at some application questions. We'll start by having a look at November 2017, Paper 1, question 3.4. Right, let's have a look at the application of vertical projectile motion graphs. We're going to start by looking at November 2017, question 3.4. Remember that we did question 3.1 to 3.3 in vertical projectile motion part 1. But we'll just quickly recap the answers we got so that they can help us to answer question 3.4. The question 3.1, we found that the time was equal to 1,22 seconds. For question 3.2, when we calculated the initial speed of stone B, we found it to be 5,98 meters per second. And finally, question 3.3, the height we found to be 43,76 meters. Right, let's have a look at question 3.4. It says, sketch a velocity time graphs for the complete motions of stone A and stone B on the same set of axes. Label your graphs for stone A and B clearly. Show the following on the graphs. The time taken for stone A to reach its maximum height. Right, remember stone A to reach its maximum height, that was question 3.1, so we have that time, 1,22 seconds. And the velocity with which stone B is thrown downwards, that was question 3.2, it was 5,98 meters per second down. So we have those values, let's get started on our graph. First things first, we're going to draw in our axes nice and accurately. Right, so this is time in seconds, and on this side we have velocity. On this side we have velocity in meters per second. Alright, so now that we have our axes, let's have a look at the motion for stone A. Remember that stone A was projected vertically upwards with an initial velocity of 12 meters per second. So we're starting with a positive velocity. And we're then going to decrease down as it got to its maximum height, a velocity of 0, and then it falls back below its initial point and on further. So let's draw that in. Right, and they wanted the time for it to reach its maximum height. We know at its maximum height, its velocity is 0, so there it is 1,22. That was for the velocity to be 0. Then we have a look at stone B. Stone B is thrown downwards, remember? So it starts with a negative velocity and then moves downwards, so its velocity is increasing downwards. Remember that our gradients for these two graphs should be the same because the gradient represents the acceleration, which for both they are under the acceleration due to gravity. So I'm going to just move my ruler so that I can see it's more or less the same. It doesn't need to be 100%, but should be as close as you can get. We start with the negative velocity, and we're going to have our graph go down like that. And remember, they asked us to include the velocity with which stone B is thrown downwards, which we said was negative 5,98. So you can also see that if we have a look where I've finished graph B, I have finished it earlier than graph A because graph B, remember, if you remember from last time, stone B hits the ground when stone A passes its initial position. So it hits the ground at 2,44 seconds, so it's about over there. We can put it in. But stone A carries on after that, so notice that graph A carries on afterwards. Remember, we must make sure we label these graphs clearly so they can see which is which. You don't need to include this time. I just wanted to show you so that you know for future reference. So that brings us to the end of question 3.4 for November 2017. Let's have a look at November 2019. Right, let's have a look at November 2019, question 3.5. Right, question 3.5 says the graphs of position versus time for part of the motion of both stones are shown below. Right, remember what stones are they talking about? We did the beginning part of question 3 in vertical projectile motion part 1. And we found these answers here. I can just remind you of some of the answers. The maximum height above the ground reached by stone A, that was 45,1 meters. The magnitude and direction of the acceleration of stone A, the magnitude and direction of acceleration for any projectile is always 9,8 meters per second squared down. And then we had to calculate the time for each of the stones, which we found for stone A, the total time was 2,79 seconds, and the total time for stone B was 1,45 seconds. And so we found, in this case, the question was asking for X, which was the difference in time, which was 1,35 seconds. Okay, so let's then have a look at question 3.5, and we can refer back to any of those answers if we need to. So here they've given us a graph of position versus time, and they ask which of the labels A to H on the graphs above represents each of the following. Question 3.5.1, the time at which stone A has a positive velocity. Well, remember, stone A was thrown up initially, so that the initial part of the motion is when it has an upward velocity, a positive velocity, and so we've got to look, but we're looking at this beginning part, and it asks the time, so we're looking at D. E, at that point, it's reached its maximum height, and so its velocity is 0. So we are looking at position D. 3.5.2 asks what is the maximum height reached by stone A? Well, our position, our maximum is A, right? There's our maximum height. It's the top of the position versus time graph, and so it is A. 3.5.3, we are looking for the time when stone B was dropped. Well, we have a look. We've got two graphs here, and stone B was this second graph, and so here it was dropped at time F. (3.5.4). They then ask the height at which the stones pass each other. Remember, if we go back to our question, stone B is dropped from the edge of the roof X seconds after stone A was thrown upwards. Stone A passes stone B when the two stones are 29.74 meters above the ground. So it's now on its way back down. So if we have a look at our graphs, we can see where the two graphs meet. That's when their position, change in their position is the same. And it asks for the height where that happens. And so we're looking at position C. That brings us to the end of vertical projectile motion part 2. We'll see you next time for the next episode.